class. We had seen the magnetic field due to a straight wire current, and after that we have seen the magnetic field due to a circular loop. Now let's see the magnetic field for a solenoid. So whenever you remember solenoid for magnetism, you should immediately remember a capacitor for electric field. A capacitor or two plates carrying equal and opposite charges was used to produce uniform electric field. Similarly, you're going to see here that a solenoid is going to be used to create a uniform magnetic field. Okay, so here, what is a solenoid? Solenoid is simply a coil of wire. It's just a coil through which you can pass current as given in this picture. So here you have a current I, and let the length of the solenoid be L. When I say length, this is L. L is a length, and let R be the radius, let I be the current through it, and let capital N be the number of turns. Okay, let capital N be the number of turns. Now here we are going to next define something called small n, and small n is the number of turns per unit length, number of turns per unit length. So small n is going to be capital N divided by L. Okay, and let's say that this is along the z-axis. Let's say this is along the z-axis. So this is your minus z, and let's say the center of it is at the origin. Then using the principle of calculus, what you can do is you can find out what is the magnetic field at some point P on the axis. You can find out what is the magnetic field at some point P on the axis. I will not get into these steps. You can actually go through it. Okay, it is simply taking a small section. Okay, maybe I'll just tell you how it's done. You will take a small section having length dz and containing a number of turns. How many turns are there? If you see, it will be n into dz. Now, because of this n into dz, what is the magnetic field at a point P? You will find out. Then you want the net magnetic field because of this entire solenoid. So you do an integration from minus L by 2 to plus L by 2. Okay, so let's not get into the steps because this is something that we have been doing over and over again and again. So straight away, I'll go to the result. So you will get the result for the magnetic field as mu naught small n I by 2 into L by 2 plus D divided by R square plus L by 2 plus D whole square minus a similar expression. And you again, I will tell you what is L. L is the total length of the solenoid. R is the radius of the solenoid. Small n is the number of turns per unit length. And what else is there? What is D? D is going to be the distance from the center of the solenoid. At a distance D, you're finding out what is the magnetic field. Okay, so therefore the D also comes. Don't worry, the expression looks a little complicated, but don't bother. Now we have to next talk about what is the direction. The direction is going to be given by the right hand rule. The right hand rule means curl your right hand finger in the direction, just as you did in the case of a circular loop. Curl your right hand fingers along the direction of the current and look at the direction of your thumb. Thumb gives you the direction of the magnetic field. Okay, and then you will ask, ma'am, is it consistent with a wire? Yes, it is consistent with a wire also. Okay, so let's just go ahead. This expression, it looks complicated, but then you don't have to remember the expression. We will get something simpler in a few minutes. So what is that? We will define what is called an ideal solenoid. We define what is called an ideal solenoid. An ideal solenoid is something where the length of the solenoid is quite large when compared to the radius. The length of the solenoid is quite large when compared to the radius. So such a solenoid is called an ideal solenoid. Okay, so let us see what is the magnetic field for an ideal solenoid. So we go back to the original expression that we got. Okay, and here use this L much greater than R. L much greater than R for ideal solenoid. When L is much greater than R, okay, it's just a simple mathematics only. You will be able to show that the magnetic field inside is going to become a simple expression. The magnetic field inside an ideal solenoid, okay, inside an ideal solenoid is going to be B equal to mu naught small n I. mu naught small n I. I is the current through the solenoid and small n is the number of turns per unit length. Okay, now you're seeing, just look at this. You're not getting L anymore. You're not getting D anymore. You're not getting R anymore. That means those dimensions are no longer coming into picture the minute it's going to become an ideal solenoid. Or you're seeing that B is independent. B is independent of R, L, D, etc. for an ideal solenoid. Or in other words, you can simply say that if the solenoid is an ideal solenoid, then the magnetic field is going to depend on the current that you are passing. It is going to depend on the number of turns per unit length. It's just going to depend on these two. And what is the direction of the magnetic field? The magnetic field direction is going to be given by your right hand rule. Or not depending on R, L, D simply means everywhere inside the solenoid, the magnetic field value is the same. Everywhere inside the solenoid, the magnetic field is the same. It doesn't depend on the location inside. Or in other words, you're going to get uniform magnetic field. So just like a capacitor plates were used for getting uniform electric field, here an ideal solenoid can be used to get uniform magnetic field. Okay, or when I say uniform, already I told you the direction is given by the right hand rule. So let's say that this is my solenoid. Let's say this is the ideal solenoid. Then you will see that the magnetic field everywhere inside will be parallel lines. Will be parallel lines. And then you will ask what happens outside. Outside, it can be quite simply shown that the magnetic field outside is zero. Okay, how do you show it is zero? Here is a picture. We'll just blow it up and show you. Let's take this picture and blow it up and show you. Okay, just look at this. Around a wire, you know that the magnetic field forms circular. That's why I asked whether it is consistent with a wire. It is consistent with a wire. You'll find that the magnetic fields are going to be given by circular loops. Now you see here, just outside, let us look at some point P outside. The solenoid is kept like this. Outside the solenoid, you take a point P and see. You're going to see that there will be a contribution because of this wire and a contribution because of wire diametrically opposite, the turning diametrically opposite. So what happens at the point P is there will be two fields, one field in this direction and another field in this direction, or the net field becomes zero. Okay, there will be circular loops because of each of these turns. So what happens is the turn at the top is going to have a current coming outside, so it will have magnetic field like this. The turning at the bottom, for the bottom turn, it's going to be a magnetic field in the opposite direction. Now both those will cancel out. So effectively you can say that if it's an ideal solenoid, outside the solenoid magnetic field is zero, and inside the solenoid it is going to be uniform and parallel to the length of the solenoid. Now look at this picture here. Ideal, the minute we say ideal, we know that there is nothing called ideal on earth. You can at most talk about solenoids which are closer to ideal. So look at this graph here. You can even just read this graph as B and the distance. So on this side, let's say it is plus Z. On this side, let's say it is minus Z. And the solenoid extends from minus L by 2 to plus L by 2. And if it's an ideal solenoid, you will find that everywhere inside, starting from minus L by 2 to plus L by 2, magnetic field value is going to be a constant. It is going to be a constant. It will just have the same value. So that magnetic field divided by an ideal magnetic field, if you just do division, you will get 1, and this 1 will be the magnetic field everywhere inside. Whereas look at the next picture, this one. Here you see that if L is going to be 10 times R, if it is 10 times R, it is not ideal, it is close to ideal. So here you see the magnetic field is uniform at the center. Starting from here to here, the magnetic field is uniform. After that, look at the magnetic field. It is falling off. As you go towards the end, it is falling off. Okay. And outside the solenoid also, there is magnetic field. Outside the solenoid also, there is magnetic field which is tapering off. Now let us go to another one which is L is equal to 4R. That means it is less ideal. Now you look at the magnetic field. Magnetic field is uniform for a smaller region. And as you go away from that, the magnetic field becomes smaller and then tapers and then becomes non-zero outside also. So always when you're working with solenoid, whenever you want a uniform magnetic field, the best thing is to go for a solenoid that is ideal. Go for a solenoid that is ideal. Okay, now I want you to just remember your Stewart Geese experiment. There you had only 50 turns, just had 50 turns only. And the radius was quite large when compared to the length of the solenoid. Therefore, the magnetic field was going outside also. Along the length, you were seeing that along the axis at 2 centimeter, 4 centimeter, 6 centimeters also there was magnetic field. That was because that solenoid was a non-ideal solenoid. In any case, you must just remember it this way. If you have a solenoid, always, if you are interested in a uniform magnetic field, place your material at the center of the solenoid. Don't go to the sides. If you're at the center, whether it is ideal or not, you know that the magnetic field is uniform. So now let's see whether you are understanding. I have some lots of messages. Let's see. Okay. Guys, I just want to make an announcement. Your practical marks are going to be shown to you after 6:10 today. After 6:10, please look for your lab marks. And then before that, don't keep going and looking at the LMS because exams are going on. You will be troubling your seniors by trying that. So after 6:10 only, you go, your marks will be displayed by that time. Okay, and people who have not done the experiment are going to be given one last chance. This 1 week window, I have put a notice. You can use it and do it. Please don't get a repeat grade don't get a report for this particular subject. Again and again, I'm insisting. That's over. And now, we want to finish the syllabus as early as possible. So tomorrow there will be one extra class that I'm taking. Tomorrow I'm taking an extra class at 11:30. I hope you're all hearing me.
Yes, ma'am.
Yes, ma'am.
11:30, because anyway now lab classes are also not there, but having two classes on the same day would be too taxing for you. So I will take it on Tuesday at 11:30. Okay, so come for the class. We will be trying to finish the syllabus as early as possible so that you can prepare for the end semester exam. Okay, so now let's try out this problem. You have a solenoid. You have a solenoid. The length of the solenoid is 1.23 meters. And look at the dia. The dia is 3.55 centimeters. So what is the radius? Radius is going to be, anyone? 1.7. 1.77, let's say. It's 1.77 centimeters. Whereas the length is 1.23 meters. Can we call this an ideal solenoid? Yes, you can. You can. You can see that the radius is small when compared to the length, almost 10 times. Okay, so you can call this as an ideal solenoid. It is nearly ideal. Because it's nearly ideal, we can straight away go for the formula B is equal to mu naught small n I. Okay, but then do I have small n? Okay, what it says is it has 5 layers of windings of 850 turns each. 5 layers. 5 layers means, let's say this is the bobbin. This is the bobbin. Those of you who have played this, what do you call that? The kite festival during Ugadi and all that. Not Ugadi, which is a festival where you use this play with kite.
Right.
Right. So when you play with kite, you have seen these bobbins, that wooden piece. Okay. So like that, please, whenever a coil is made for a solenoid also, there will be a bobbin. So what is first done is, there will be one layer of the wire. There will be one layer of the wire starting from here and ending here. And then again, one more layer on that, like one more layer. So here he says there are 5 layers and 850 turns. So what is the total number of turns? Each layer is having 850 and 5 layers are there. So total number of turns will be 850 into 5. Okay, so 0, 25 to 42. So 4250 layers will be there. But what is small n? Anyone? 4250 divided by length. What is the length? Length is 1.23. So that will be the number of turns per unit length. So substitute mu naught is 4 pi into 10 to the power of minus 7, and then 5 into 850 divided by 1.23, which is what I showed you here, into the current. The current is 5.57 amperes. Okay, so you will get your magnetic field as 24.2 milli Tesla. You get your magnetic field as 24.2 milli Tesla. Now the question is, have you at any time come across an electromagnet? Have any of you at any time come across an electromagnet? Anywhere? Have you come across a term electromagnet? Okay, well, if you have not, I think you're never going to hear it again. Okay, let's just now go ahead with the syllabus and talk about Ampere's law. So Ampere's law is analogous to Gauss law. Ampere's law is analogous to Gauss law. Before Gauss law, you studied Coulomb's law. Coulomb's law merely told you what is the electric field because of some point charge. Okay, and then we use symmetry and then found that we don't have to do this integration, we don't have to do calculus. Without doing all that, we can get the same electric fields just by using Gauss law. Similarly here, you have found out that with a current carrying conductor, you can produce a magnetic field. For a random current carrying conductor, you found out what is the magnetic field at a point. That is Biot-Savart's law. After that, using Biot-Savart's law, you found out the magnetic field because of a wire carrying current. Then you found out the magnetic field because of a ring of current. And then you found out the magnetic field because of a solenoid. And in all these three cases, you took a small current element, found the magnetic field dB at a point, then you did an integration. It is cumbersome. So now we will use something simpler. So what is that simpler thing going to be? That simpler thing is going to be your Ampere's law. So in Ampere's law, you're going to use the symmetry of the current and the magnetic field. In Gauss law, you use the symmetry of the charge and the electric field. Here it is, current and the magnetic field. Now before we do that, can we not talk about a Gauss law for magnetism? You know Gauss law for electric field is electric flux is integral E dot dA is equal to Q by epsilon naught. Similarly, if one were to write an expression for magnetism, it would have been integral B dot dA equal to, what do you write on the right hand side? On the right hand side, it will not be possible to write anything because you know that there are no isolated magnetic monopoles. You don't have a separate north pole and a south pole. Whereas in electrostatics, you have something called positive charge and negative charge. Here you don't have that luxury. So it just becomes zero. It just becomes zero. Okay? Because there are no isolated magnetic monopoles. And then every time the magnetic fields form closed loops. They form closed loops. So if I take a volume, I have a magnet inside. And then if I take a volume around it, the number of lines coming out will be same as the number of lines coming inside. And you know, flux is always is represented by the number of lines cutting through a surface. Since the number of lines cutting in and out are going to be equal, the flux is going to be zero. Therefore, Gauss law for magnetism is going to be this equation. It's not going to help you determine the magnetic field. So this is where we go to Ampere's law. And please remember, just as we talked about Gauss law being a more fundamental law, which becomes one of the Maxwell's equation, here Ampere's law is also a more fundamental law, which will get into Maxwell's equation. We use symmetry. Okay, and remember, Biot-Savart's law is not Maxwell's equation. Similarly, Coulomb's law is not Maxwell's equation. So now let's quickly see what is this Ampere's law. In Ampere's law, we will do a line integration. It is not a surface integration. We will be doing a line integration. So the line integral of the magnetic field around a closed loop is equal to mu naught times the net current cutting through the area enclosing the loop. The area enclosing the loop. This is called Ampere's law. Let me show you what it means. Let's say I have some current I1, I have some current I2, I have a current I3. And if I'm going to have a loop, I'm interested in finding out the magnetic field at this point. So what I will do is I will construct an imaginary loop. I will construct an imaginary loop around it. Okay. And I know that at every point on this loop, there is a magnetic field given by these three wires. But I don't know what is the magnetic field. The magnetic field at this point may not be the same as the magnetic field at this point. At different points, the magnetic field may be different. But what we do is we do a line integration. We'll do a line integration over this loop. This is a closed loop surrounding the source currents. Okay, and then this is a closed loop. Therefore, you will write it as integral B dot ds. He's using ds, not dl. I have this confusion because for the third year paper, they write dl. Okay, integral B dot ds for this closed loop will be equal to mu naught times the sum of the currents. Okay, the sum of the currents in this case is I1 plus I2 plus I3. So this is what is Ampere's law. Okay, and please remember this loop that you have put here is called the Amperian loop. This is called the Amperian loop. And I1 plus I2 plus I3 is the net current enclosed by the Amperian loop. Here it is quite simple in the picture I have given you. Okay, I wrote I1 plus I2 plus I3. All three are parallel currents and they are cutting out of the loop. If I am having an imaginary surface, enclosed by the loop, let's say this is my loop. Okay, and if I say that there is a surface which is enclosed by the loop, and if my currents I1, I2, I3 are cutting through this area, then I can add this I1, I2, I3 and multiply by mu naught. I will get integral B dot ds. But in doing that, I have to have a caution. Okay, what is that caution? Let us see. Let us look at the next picture. I hope you're able to see the picture. Here is my loop. This is my loop. Okay, you can see that light pink, which is a surface enclosed by the loop. And see here you are having a current. You have a current I1 which is going out upward. There is a current 2 which is coming down. Then there is a current I3 which is outside the loop. There is a current I4 which is not cutting the area. There is a current I4 which is not cutting the area. Now in this case, what should I do? What I have to do is, I have to decide what is going to be the direction of my integration. I want to do my integration like this or I want to do my integration like this. That I have to decide. And then use another right hand rule. Again, there is a right hand rule. So many right hand rules you will have. Again, there is a right hand rule. What is that right hand rule? Right hand rule. Curl your right hand finger in the direction of your integration. Curl your right hand finger in the direction of the integration and look at the direction of the thumb. All currents which are going to cut through the surface and go up like this, they are positive. And all currents which are going to go in this direction with respect to this integration is going to be negative. So by that logic, what happens is you will see that I1 is positive, I2 is negative. Therefore, you will write mu naught I1 minus I2. I1 is positive, I2 is negative. What happens to I3 and I4? I3 and I4 are not cutting that light pink surface. They're not cutting through the light pink surface. So you don't have to consider them. You don't have to consider them. Okay? So that's the reason why you have to only consider the currents which are enclosed by your Amperian loop. And again, use the right hand rule to decide which are the positive currents and which are the negative currents. Now here there is a question. Why are currents outside not contributing? Here is a question. Why are currents not enclosed by the loop not contributing? That is a question. For that, I'll give you an answer. Let us consider this current, I3. If you take this I3, okay, this is I3. Now, let's say this is I3 looking down. Okay, now You know that you look at that loop and see, for part of the loop, the magnetic field will be like this. For the other part of the loop, the magnetic field will be in the opposite direction. Okay, the magnetic field will be part of the loop, it will be in one direction. For the part of the loop, it will be in the, or in other words, I shouldn't say magnetic field, I'll say that integral B dot dl. I'll say integral B dot dl for part of the loop will be positive and for part of the loop, it will be negative. Like for example, uh, here, this is like this. So here what happens is integral B dot dl, B will be in this direction, dl will be in this direction, therefore negative. When you come here, what happens is, okay, B and dl are going to be in the same direction, therefore positive. This will be negative and part of it will be negative, negative and positive. So the net integral, if you see, it will be 0. Okay, and let us look at I4. Why it is not contributing, let us see. Actually, I am interested in finding out integral B dot dl for the closed loop. I have a surface. Now, who says that the surface has to be straight like this? I'll give you an example. If I take a torn balloon, I'm sure all of you have played with balloons when you were small. The balloon bursts. After that small piece, I'm sure all of you have played this. You will keep it on your mouth and then blow. I'm sure all of you have done that. You will keep it on your mouth and then blow. Imagine your mouth to be that line integral. Okay, and your mouth, when you blow out, the balloon surface comes like this. Or when you suck it in, the balloon surface goes like this. Okay, that is not going to change integral B dot dl. Integral B dot dl is just going to depend on what is that contour only. Okay, so in the second picture, what we have done is look at this. You've blown that pink surface so that it encloses I4. You've blown it so that it encloses I4. But you see here, it is once going in and once going out. So that means it is I4 minus I4, 0. So that is your interpretation that this current is not going to contribute to the magnetic, it is not going to contribute to the integral B dot dl. Okay, now integral B dot ds, these things you can just go through. Okay, this is exactly like Gauss law, you can go through. Instead, I would spend more time in working out the exercises. That will be more useful for you. Okay, one important thing that you should see here is that when you did electrostatics, we have seen that the work done for a closed loop was equal to 0. Work done for a closed path was equal to 0. That's how we talked about conservative forces. Okay, and work done is after all Q into E F dot ds. So Q into integral E dot ds for a closed loop equal to 0. And we said it is a electric field is conservative. But look at our magnetic field. In magnetic field, integral B dot dl, sorry, integral B dot ds, integral B dot ds, if you see, it is not equal to 0. So what do you conclude from here? You can conclude that magnetic field is non-conservative. Magnetic field is a non-conservative field. That is the reason why magnetic forces are also non-conservative, whereas electrostatics, electric field is conservative. Okay, I told you why I just skipped those 3 steps. I want to spend more time here. Let's look at the applications of Ampere's law. So the first application is going to be finding out the magnetic field because of a thin straight wire, a thin straight wire. So here is our wire. Here is our wire. Obviously, you can't put a dot like that. So this wire is actually perpendicular to the plane. It is perpendicular to the plane of the screen. Okay. And there is a current I. Let's assume it's a uniform current. It is coming out of the screen. You want to find out the magnetic field at some point here, at a distance d. So from the symmetry, you know that for a straight wire, magnetic field will form a closed loop that you have seen in the beginning of this chapter. Therefore, from the symmetry, your Amperian loop will be a circle. The Amperian loop will be a circle of radius d, so that the point of interest is lying on the Amperian loop. And then use your right hand rule. From right hand rule, I know that the magnetic field at every point is going to be given like this. And at every point, you know that the magnetic field value is going to be the same. This also you got at the beginning of the chapter. So what you do is, you take your B vector here, B vector, and also look at the DS vector. You find that the B vector and DS vector will be parallel to each other. Okay, B and ds vector will be parallel to each other. So now let us do integral B dot ds. Integral B dot ds will be B ds cos 0. Cos 0 because they are parallel. Cos 0 is 1. And then B is going to have the same value for the entire circle. At every point on the circle, B is going to have the same value. So take out B out of the integral. So you get equal to B into integral ds. And what is ds? ds, if you do the integration, will be the circumference of the circle, or it will be 2 pi d. And what is on the right hand side? Right hand side is mu naught into I. Okay, therefore, take 2 pi d to the other side, you get d is equal to mu naught I by 2 pi d. Okay, here in green letter, I have given an exercise which I want you to try. Now let us try the magnetic field because of a long straight wire. Again, it's a long straight wire, but this time the wire is going to have a definite radius. The wire is going to have a definite radius. In the first case, it was a thin wire. We didn't bother about inside the wire. It was a thin wire. Here it is a slightly thicker wire. The radius is R. Radius of the wire is R. Okay. And now you are interested in finding out the magnetic field at a point inside and at a point outside. You want to find out the magnetic field at a point inside and then at a point outside. Again, symmetry tells you that the magnetic field has to form closed loop given by the right hand rule. So our Amperian loops will be circles. Like in Gauss law, here also, whenever you're drawing Amperian loop, use dotted lines. So first, and then let's also assume that it is a uniform current. Let's assume it's a uniform current. So that means this is the thickness of my wire. All through my wire, the current value is the same. At every point here, it's equal amount of current is flowing. So it's a uniform current, which means it's uniform current density. So let's find out at a point outside. At a point outside, let's get the magnetic field. So make your Amperian loop. And let us say that the current is out. Let's say that the current is coming out. Okay, this is the current. So use your right hand rule. Okay, so then your B is going to be this. Your ds is also going to be parallel. And B is going to have the same point, same value everywhere on the circle. So integral B dot ds becomes B ds cos 0 or B ds, B comes out of the integral. So B into 2 pi r equal to mu naught I, or B equal to mu naught I by 2 pi r, same as for a thin wire. Here we said r is the distance. R is a variable. You can take any distance outside. Only thing is small r is greater than or equal to capital R. That means outside the wire, you take a point outside, the magnetic field is inversely proportional to the distance. As you move away from the current wire, magnetic field is falling off. Okay. Now let us see what is a magnetic field inside the wire, or for R less than capital R. So here we have taken a point at a distance small r less than capital R. Once more, draw your Amperian loop. Again here we will say that the ds vector and the B vector are parallel to each other. So integral B dot ds becomes B into 2 pi R. But what about the right hand side? When you come to the right hand side, you have to see that you have to consider only the current enclosed by the Amperian loop. Current enclosed by the Amperian loop. So how much is the current enclosed by the Amperian loop? That is the current which is inside the Amperian loop. All the current which is inside this area of the wire, not the complete wire, the area enclosed by the Amperian loop. How much is the current flowing here? You have to just take only that much current. Let's call that current as I prime. You know that a current I is flowing in an area pi capital R square. That is a full current in the full area. And a current I prime is flowing in an area pi small r square. Okay. So from here, you can get your I prime as I into, take your pi r square that side, I into small r square by capital R square. Okay. So we are going to use this and then take the 2 pi r down. So therefore you will get B equal to mu naught I small r by 2 pi capital R square. Mu naught I small r by 2 pi capital R square. So what are you seeing here? Here you're seeing that magnetic field is directly proportional to R. That means if you take a uniform current, as you move away from the center, the magnetic field is going to become larger and larger till you reach the. Why is it becoming larger? Because more and more current is getting enclosed. Current is the source of the magnetic field. But once you reach the surface, that is the maximum magnetic field. After that, when you move away, magnetic field falls. So that's demonstrated in this particular graph. B proportional to R till you reach the surface. After that, it falls off as 1 by R. Okay, so you can see that whatever you did in the last class using calculus has become simple here using Ampere's law. Okay, now let's go back to solenoid. Now you'll understand why I didn't want to do that stupid mathematics. Okay, so here is my solenoid. From that, we knew that for an ideal solenoid, magnetic field is going to be parallel, uniform, parallel to the axis and uniform. So here is a picture. These dots, it's as if, you've taken a solenoid and then slit it into two, slit it, and you're seeing the cross section. So here the current is coming out of the plane and here it is going inside. Okay. And using your right hand rule, you know that the magnetic field is going to be this. That's why the magnetic field is given as B, uniformly spaced and to the right. So now you are interested in finding out the magnetic field. You know that this is what the magnetic field is, but you want to find out the magnetic field. So let's say you are interested in finding out the magnetic field at some point inside. At some point inside. So what we'll do is, let's say we are interested in finding the magnetic field here. Okay. So now you're going to, from the symmetry of the problem is that the magnetic field is uniform everywhere inside and zero outside. It's an ideal solenoid. So take a rectangular Amperian loop. The Amperian loop that you're going to use is going to be a rectangle. And let's call this rectangle as ABCDA. ABCDA. Okay. And let us do our integration. Let us do our integration. If you do your integration, only you can divide this integral into 4 parts. A to B, B to C, C to D, D to A. Okay. Now, C to D will give you 0. C to D will give you 0 because the magnetic field is 0. Now, let's come to these two perpendicular paths, BC, DA and BC. In both these places, what happens is B will be perpendicular to DS. B will be perpendicular to DS. Because B is perpendicular to DS, it will be sorry, what did I say? Yeah, it will be cos 90. Cos 90 is 0. Therefore, these two fellows also will give you 0. So that leaves us with just AB. Just leaves us with AB. And if you look at AB, okay, the length, let us say the length of this rectangle is H. Okay, and at all points on this rectangle, the magnetic field value is B. It's a constant. So integral B dot ds will simply become B into H. Will become B into H. All other things will become 0. Now, what about the right hand side? When you go to the right hand side, you have to see mu naught into the total current enclosed. So let us say some number of turns of current are there. Each turn is carrying a current I. Now, how do I find out how many turns are there? I know that N is the number of turns per unit length. The length that I am considering is H. So H into N into I will be the current. I hope you are getting the logic. I is the current through one wire, but then there are small n into H number of turns. So the total current is N into H into I. And all these currents are positive because of my right hand rule. Okay. So I'm ultimately getting B into H on the left hand side is equal to mu naught into small n into H into I on the right hand side. H and H cancels out and you get B is equal to mu naught small n I. Quite simple. Now, this is the last part of the syllabus. We are going to find out how to get the magnetic field for a toroid. A toroid is something that in a dimmer stat, I don't know, you will come across a dimmer stat later. A dimmer stat, for example, will have coils. Okay. Or I'll tell you what is a toroid. Toroid is simply a solenoid which you take and you just bend it and make a circle. If you take a solenoid, okay, imagine a solenoid, and let's say you are able to bend a solenoid and make a circle out of it, then that is a toroid. Okay, so let's consider a toroid. So here is a picture of the toroid given to you. Toroid is also used to create magnetic field. Okay, so let there be capital N number of turns. It is bent in the form of a, yeah, beautiful. It's a donut. I'm sure all of you know a donut. It will look like a donut. And you have to now talk about what, let's say that A is the inner radius, and let's say that B is the outer radius. Okay. From Ampere's law, you can straight away say that B is going to be zero inside. How do I say that B is zero inside? I say that B is zero inside because if I take any Amperian loop like this and see, there is no current enclosed. There is no current enclosed. So everywhere inside, the magnetic field is zero. Similarly, I can take an Amperian loop outside and show that magnetic field is zero outside. How do I do that? B into 2 pi r is going to be equal to capital Ni minus capital Ni into mu naught. Why am I putting this? Can someone explain? Mu naught into capital Ni minus capital Ni. Why did I put that? Because look at this. There are n number of currents, n number of turns coming out of the screen and n number of turns going inside. Okay, so if one of them is positive, the other is negative. Therefore, the net current through the loop is zero. So therefore, you can say that B is equal to zero outside and B equal to zero inside. That means somewhere between these two, between A and B, magnetic field is not equal to zero. So we have to find out what is that magnetic field. You know that if you take a solenoid, the magnetic field is parallel to the axis. So if I take the solenoid and then bend it into a circle, magnetic field also will become a circle. Magnetic field also will become a circle. So let us say the magnetic fields are circular loops with a direction as indicated here. Okay. So now I want to apply Ampere's law. Okay, so we will take an Amperian loop of radius r, so that that point is lying, and then take your Amperian loop as a circle. Okay, everywhere on that circle, magnetic field value is going to be the same. Do your integration B dot ds. Okay, if you do that, you get integral B dot ds is B ds cos 0, which is B ds, which is B into 2 pi r, equal to mu naught into capital Ni. Mu naught into capital Ni. So this is my magnetic field. All the currents which are going into the screen are positive currents. And there are n turns, n number of turns, each carrying a current I. Therefore, Ni. Or I get my magnetic field as 2 pi r, you bring it this side, you get B is proportional to 1 by R. B is proportional to 1 by R. And there is magnetic field only inside the hollow of the solenoid. Outside it is zero, inside also it is zero. Only inside the body of the solenoid, there is only inside the body of the toroid, there is a magnetic field. Next thing is, when as long as it was a solenoid, magnetic field was uniform inside. But here, the minute you bend it into a toroid, the magnetic field depends on the distance from the center. It is not uniform. It depends on the distance from the center. Okay, so with this, we are winding up this chapter. And you can see that Ampere's law makes your job really easy. So what I want you to do is, go through this. There is a fourth quiz. I hope you know that. Do you know that there is a fourth quiz?
Yes, ma'am.
Yeah. So what do you think will be the syllabus? What did we cover in the last quiz? Until which chapter did we cover? 30? 32. Okay, so this time it will be 33 and 34. 33 and 34. So as soon as 34 gets over, you will have your quiz, which is the reason why I want to have a special class tomorrow, because I don't want to because syllabus is a lot. We can go on, if we actually go slowly, till 2nd of next month, I will be taking class. And from 5th, you are having your in-semester examination. I don't want to tax you like that. So let's quickly finish it. Let's finish the components. Look here, lab also. We are going quite on time. Everything has gone well. It's over. Similarly, our components are all over. Your midsem grading also, madam will put it up this week. In tomorrow, day after tomorrow, she will put that on LMS. Then we have only one quiz to complete. That we will finish as soon as chapter number 34 is over. So that way we will be completely ready. Everything from our side will be over. You have to just prepare for the end semester examination. So that's the reason why I want you to stretch a bit. Towards the end, you may have a lot of submissions, a lot of other things will be there. I don't want to tax you at that time. So tomorrow, let's have one special class. I will start with chapter number 34. Quickly, let's finish off 34. You can have your quiz also immediately. Okay?
Okay, ma'am.
Yeah, tell me. Somebody is asking something? Yeah. Today, after 6:10, go to LMS. Your marks will be there. You can see that. Okay. And after you see your marks, those of you who have to repeat some experiment, COVID and such guys also, please do it and make your submissions. But one warning I want to give you, don't do the same experiment and put it in different places, because we will be downloading it, we'll be opening it. So don't do such things. If anybody is found doing such things, it is a 0 mark. If you go to LMS tomorrow, today evening, go to LMS. There you will see the experiment numbers are also given. In case somebody has missed some experiment, please complete the job and then submit. Anything else you want to ask? Okay, if nobody has anything to ask, I think I'll leave now.